My name is Ugo Simeoni, and I'm a Research and Innovation Manager at European Turbine Network. It is welcome. It is really great, to welcome you here after the success of the first episode. It's already 1 month since we have hosted the first discussion and that happened between the European institution and the private sector, focused on the role that centralized power generation and in particular fossil fuel power plants plays in the EU energy scenario. But before I carry on with my introduction, I would like to welcome our today's speaker, Ms. Alessandra Cuneo, the Technical Project Coordinator at Rina Consulting, Ms. Paula Ramos, Senior Expert and Strategist on Management System Integration at EDP, Mr. Denis Thomas, Global Business Development Leader, Water Electrolysis at Cummins, and Mr. Pascal Koschwitz, Researcher at Technical University of Darmstadt. What all of our speakers today have in common is that they are all part of the Horizon 2020 project FLEXnCONFU, which stands for FLEXibilize Combined Cycle Power Plant through Power to X solution using non-conventional fuels. Indeed, after having laid the foundation of our discussion on flexible power generation during the first episode of this series, from today and for the next months, we will explore technically how power plants can become more flexible. So to do so, in each episode, we will analyze different ways to increase the flexibility through the 5 Horizon 2020 projects. And FLEXnCONFU has the honor and also the burden to be the first featured project. But before our speakers goes into the technical details of the Power to X solution, I would like to say a couple of words more regarding the reason why FLEXnCONFU is important today. So as we all know, Europe is working on a decades-long decarbonization path, focused also on increasing the EU energy independency by an increased share of renewable energy sources and of decarbonized fuels. So flexible power plants would be ideal to compensate the intermittency of the renewable energy sources, and by using also hydrogen and ammonia as non-conventional fuels, then they would reduce also their greenhouse gas emissions. And so making the power plants also more environmentally friendly. At the same time, Power to X solution, and in the specific, the one that we will see now in the FLEXnCONFU projects, will allow to level the load of the combined cycle power plants, and at the same time ensuring the security of energy supply. So now, without any further ado, I would like to leave the stage to our first speaker, Ms. Alessandra Cuneo, who is here as FLEXnCONFU's project coordinator. Alessandra, could you give us a general introduction to the project, please?
Yes, so good morning, everybody. Thanks, Ugo, for introducing me, and thanks to all in organizing this webinar series. I'm glad today to be the first project to be presented related to flexibilization of power plant. And personally, I'm Alessandra Cuneo. I'm a project coordinator at Rina Consulting, and I am the project coordinator of FLEXnCONFU project. So I will give you a brief overview of the project objectives, the consortium, and activities that we will perform in the next 3 years and a half. And my colleagues from EDP, from Cummins, and from Hydrogen, and from Technical University of Darmstadt will give you more detail on some technical aspects related to FLEXnCONFU project. So the project is started in April this year, so just 6 months passed from its start, and it is 4-year project, so we will have all the results and the evaluation of the impact of the project in 3 years and that for now. The project is about 10 million euros funding, and the consortium is composed by 21 partners. Which are the drivers of FLEXnCONFU project? So why we are working on this European project? The aim is driven by 4 main aspects. The first one is related to the fact that the natural gas is taking a major role in the European energy system, but we would like to, there is a trend to decarbonize the energy scenario in 2050. So the natural gas power plants are one of the main technologies that could be the bridge, bridging technologies towards the decarbonization of the energy system. The second driver is related to the use of the hydrogen, which is currently more and more present in and considered an essential element in the energy transition, and that can achieve an importance in the future European economy. Nowadays, I imagine that most of us are working on hydrogen aspect. The third driver is related to a trend use of hydrogen and we will see how ammonia as a combustion fuel in gas turbine. So the aim of the project is to become one of the reference points in the short term, more related to the hydrogen part, and in the long term, more related to the use of ammonia as an energy carrier. And the last driver is related to the fact that the variable generation is rapidly grow, and there is a need to have more flexible power plants and storage technologies that can partially that can help the variable generation of the renewable energy sources. The fact that power to gas technologies are receiving more and more attention in Europe as one of the possible storage that could be coupled with renewable energy sources. So the aim is to replicate our power to gas solution that could be applied in the energy field, but and in our project in the fossil fuel power, integrated in fossil fuel power plants, but can be applied also in other energy sector in order to enable and to help a higher penetration of renewable energy sources in our system. Which is the goal, the aim of FLEXnCONFU. The aim is to demonstrate at TRL 7, which means that a prototype will be really integrated in a real operative plant, which is the power plant managed by EDP in Portugal, the Ribatejo power plant. So what we would like to demonstrate an integration of power to X to power solution that are able to increase from one side the fossil fuel, the fossil-based power plant flexibility, so to increase the flexibility of the power plant, and at the same time to reduce the emission of the power plant itself. And how we would like to do that? The aim is to demonstrate a power to X to power system that is based to non-conventional fuel. And from one side, we will demonstrate power to hydrogen solution, and that is the one that we will develop and deploy in the real operative plant. But on the other side, we would like also to exploit the potential of the ammonia, both as energy carrier and as a combustion fuel. And to do that, a prototype of power to ammonia to power solution will be tested in a laboratory in University of Genova. And in parallel to all these activities related to the power to X solution, there will be also some research on combustion part. This is not the main aim of the project, which is more related to the power to X solution, but of course, if we would like to integrate this solution, this system in power plant, and to reduce the via power to X system in the power plant itself, we need to study and to understand also the combustion of the hydrogen and or ammonia. And so thanks to the Cardiff University Combustion Lab, some combustion tests will be performed mainly related to ammonia to understand all the problems related to the combustion. And the aim both at Cardiff University Combustion Laboratory as well as in the power to ammonia system that will be developed and installed in Savona, the aim is to reach 100% of ammonia combustion. The project is based to 4 main pillars. The first one is related to the use of non-conventional fuel to increase the flexibility and to increase as well the environmental sustainability of the power plant. So in particular, as anticipated you, hydrogen and ammonia will be studied as potential fuel to be used in power plants instead of natural gas or in a blending with the natural gas. The second pillar is related to the integration of the demonstration of such power to X system in real power plant. 1 megawatt electrolyzer will be installed integrated in power to hydrogen solution in Portugal. So the hydrogen will be stored and reused in the same power plant based on energy market needs, energy market constraints. The third pillar is related to the development of proper grid-oriented control strategies. So it's needed to develop a dynamic model of the system and define proper control strategies to control the electrolyzer to store ammonia and or hydrogen, and decide when reuse such fuel in the gas turbine. Of course, all these controls are strictly correlated to the needs and to the constraints of the grid and, of course, of the energy market. Pillar is related to the promotion of an hydrogen and ammonia energy society. So the idea is to have a clean, affordable, and reliable energy system in Europe. The demonstration will be occurred at 4 different levels. First of all, some combustion studies will be performed by Cardiff University in their laboratory, in which both hydrogen and ammonia combustion will be studied. Then we will have 2 demonstrations. The first one is at TRL 6, related to a power to ammonia solution that will be demonstrated in Savona, and in particular a power to ammonia system composed by an electrolyzer, an ammonia synthesis reactor, and ammonia storage will be integrated in an existing microgas turbine that will be properly modified to inject ammonia in the combustion chamber. So the combustion chamber will be redesigned for the ammonia combustion. And then we have the real demonstration in Ribatejo power plants in Portugal, in which a power to hydrogen solution composed by 1 megawatt electrolyzer and an hydrogen storage, together of course with all the other components such as the hydrogen compression and the part related to the injection in the combustion chamber, will be demonstrated and managed by EDP. And then, of course, we don't want only to focus on the 2 demonstrations and that we have in the project, but of course also to demonstrate the potential replicability of our solution. And so we already engaged 2 virtual demonstrations. One is managed by Tirreno Power, which is an energy utility with a power plant in Savona, in Italy. And the second one is a power plant managed by ENGIE in Belgium, in which we would like to virtually demonstrate FLEXnCONFU system towards, of course, the maximization of the replication potential. So this is just a brief slide to demonstrate you the time plan of our project. So it started in April this year. We just finished the first 6 months of the project, and we started to discuss on the layout, so the layout of the single power to gas solution and how to integrate this system with existing power plant. So we are in assessment phase. Then, of course, in 1 year and a half from now, we will start the development and the pre-demonstration phase, in which all the components will be installed in the 2 demo site towards the demonstration phase. And in particular, the 2 systems will be operative and monitored in the last year of the project. And of course, all the technical parts related to the development and the deployment, the installation of the power to gas system in our power plant. In parallel, we have all the activities related to the environmental assessment, to the replication, and to the promotion and the policy aspect, because of course we need to consider also not only all the technical constraints and needs, but also all the regulatory framework and the policy and the legislative constraints. The consortium is composed by 21 partners. It's really industrial driven, and we have partners that cover the whole value chain of FLEXnCONFU. So we have gas turbine OEM, we have energy utilities, we have power plant operator, we have, of course, dissemination partner, and we have partner with capability related to the ammonia combustion, to the power to ammonia system, and to the power to hydrogen solution.
Alessandra, can I ask you to finalize the presentation?
My last slide. So the impact of the project, as anticipated and as I show you in my presentation, is related to contribute to have a more secure and resilient power system through the integration of power to X solution. And the aim is to leveling and try to help the existing power generation. To do that, of course, we aim to have impact on the power plant related to the reduction of the minimum load, to increase the efficiency, to reduce the number of startups, and to have quicker ramp down. So to make existing power plant more flexible. And of course, all these activities are related to help the current energy system to be more adequate and to be adapted to the dominate scenario in which the intermittent renewable energy will have and already have a huge contribution to the current energy system. So that's all. You can see here my contact, and we encourage you to follow us on website and on our social media. Thanks.
Thank you, Alessandra. I see in the chat we have one question that maybe we can take before we go to the next speaker. Is what will be the goal for the NOx levels? Okay, so the goal, of course, the NOx is a problem when we talk about ammonia and hydrogen combustion. And the problem on NOx will be deeply analyzed in the combustion laboratory at Cardiff University. For the moment, we do not have a sort of goal. Of course, we would like to evaluate the NOx emission and evaluate and study the possible the NOx system solution. And we will follow during the project what happened and the discussion in Europe about this topic. So for the moment, there is no, how to say,
standard or constraint to be followed on hydrogen combustion or ammonia combustion is something that is currently ongoing, and we follow regulation, etc., and we deeply analyze the emissions and try to define proper system to decrease them.
Okay, thank you, Alessandra. Thanks a lot. Maybe other questions we can take after all the presentation towards the end of this panel discussion. I would like now to give the floor to the second speaker, Ms. Paula Ramos, Senior Expert in Strategies on Management System Integration at EDP, the Portuguese electric utility. So before just leaving the floor to Paula, can I ask to all the participants to switch off the video so that we may have a better connection and more stable connection. So Paula, the floor is yours. You can present your slides.
Thank you very much for this invitation and for your introduction, Hugo, and to address this actual subject of to FLEXibilize the conventional power plant in the context of high penetration of renewables and fuel transition, where hydrogen can have definitely an important role for decarbonization. So are you seeing my screen? Sorry.
No.
No?
Okay, if you...
Are you seeing?
Yes, now yes. If you scroll the slides, okay.
Okay.
Perfect. Yes.
Okay. Okay. Let's proceed. So, first, just a few words about EDP Group. With a significant presence in the energy world, EDP Group is in 16 countries, has around 12,000 employees of 44 nationalities, more than 11 million customers, and an installed capacity of 27 gigawatts. More than 10 gigawatts of this power comes from wind farms installed in Europe, Brazil, and North America, being one of the leading global players in renewable energy. EDP Produção is the EDP Group company responsible for generation in Portugal, managing more than 60 hydroelectric and 4 thermoelectrical plants, representing 10 gigawatts total capacity installed, and leading the supply of energy throughout the country. 68% of our installed capacity is hydro energy, and the remaining 32% on conventional thermal power generation. EDP is also defining its strategy in hydrogen and is actively developing several initiatives and studies and feasibility studies of on offshore electrolyzers on offshore. And one of our project is this power to hydrogen in Ribatejo FLEXnCONFU project, H2020 demo project. And we are also involved in a big project for H2 Teschnische to create an hub of hydrogen production. Talking about our FLEXnCONFU project, the main goal is to test in a full-scale power plant the solution of power to hydrogen to power. Ribatejo is a combined cycle power plant located on the right side of the Tagus River, of about 30 kilometers northeast of Lisbon. The power plant comprises 3 similar and independent units burning natural gas. The total capacity installed is 1,200 megawatts, and the unit is in operation since 2004. The FLEXnCONFU project consists of installing one fast cycle electrolyzer, PEM technology, producing about 250 normal cubic meters per hour of hydrogen. Then the hydrogen is compressed and stored at 200 bar, and for further injection in the natural gas pipe that feeds the gas turbine. The concept is to produce hydrogen when there is excess of energy, not dispersed, so the unit is in a ramp down. Storage the hydrogen and burning further to produce power again when demanded by the grid, so the unit in the ramp up mode. So this can be valuable for grid balancing and or ancillary services to supply to the grid. The main goals are to inject 1% of hydrogen, evaluate the gas turbine compatibility with burning other fuels, explore the energy storage concept through this hydrogen carrier, explore the energy, this energy storage, and verify the benefits in terms of wear and tear reduction, avoiding these constantly starts and stops due to this penetration of the renewable, and looking for the efficiencies and the emissions, of course. We will collect all these parameters, these operational parameters, efficiencies, load ramps, and so on, to set up as a design parameters for the scale up. The project is in development phase, as Alessandra already referred. The construction and installation phase will start at the end of the next year, and the demo will be in operation in of April 2023. The last year will be totally dedicated to the demonstration, and we hope to testing 1,000 hours. Then to implement in this development phase, to implement a project like this, there are 4 main aspects that we have to look. The site, the technical aspects, the safety, and the regulatory. The site constraints and space availability is always challenging in retrofits, and we will see on the next slide in particular. Regarding technical aspects, the gas turbine assessment is critical. Using hydrogen in gas turbines, what are the percentage of hydrogen that we can inject? What are the modifications that these gas turbines need? So we have already done a benchmark through the main original manufacturers, and all have heard that below 5%, there is no need of big technical modifications. So the gas turbine, only modifications regarding engineering and control system and risk assessment are needed, but maybe an hydrogen analyzer may be required. It's quite a little bit expensive also. Between 5 and 50%, no technical modifications, big technical modifications, but there is some modifications at the level of the burners that should be addressed. Between 15 and 30% hydrogen injection, there is a major intervention in the gas turbine is required, and can spend several millions. And above 30% not yet in available commercial phase. So there is the burners are under development. So another aspect to address here is to look for the electrolyzer, of course, the technology, the maturity of the technology, alkaline, PEM, the compressor, the insights, how to compress, how to storage these. The BOP, the balance of plant, is also an aspect that we should assess. We have to assess. So how to see how all the requirements needed for these new systems, and how to integrate these in the power plant. So to see all the battery limits, to see the requirements regarding the water, nitrogen needs, cooling water for the system, compressed air, firefighting. So everything should be addressed and integrated in the best way in the existing power plant. Then the safety issues, the assessment of the safety requirements to fulfill the standards and the rules are mandatory. A tech study is mandatory, as well as a risk analysis and as-it-as-of analysis is mandatory to implement a system like this in safety. And the final, the licensing, the licensing that is needed, regulatory aspects, licensing permits, not just before the implementation, but also during the implementation. We need licensing for constructions, licensing for the project of electrical project, firefighting project. Seveso directive has to be addressed. So all these aspects regarding licensing should be addressed, and even for bigger, not pilot, but for bigger installations, an environmental study is needed, is required, and this is a process that should start, spends a lot of time, so 24 months is needed to have these licenses. So this is a spec that should be taken carefully. Regarding the challenge of the layout, besides the gas turbine assessment and the protection of the gas turbine, the space required for installation could be challenging, especially in this kind of CCGT plants that usually are very compact. So there is not available a lot of space. Here is the plant of the Ribatejo. Choosing the best location. This means that not only space available, but this should be in full compliance with the safety requirements, namely respecting the distance from the neighborhood facilities, or include some additional protection, walls, concrete walls, and so on, to respecting the strict rules of NFPA, and to maintain the safety regulations and the safety aspects. And also the storage here, what is the capacity, the necessary capacity. Here we have already made an exercise for a minimum load. If we go to a minimum load in a big plant, for a minimum load to the combined cycle power plant, in this case, for instance, the minimum load in Ribatejo is 200 megawatt. Based on this, we study different storage capacities. We're thinking of a storage capacity for 48 hours and for 8 hours. And what we found is that to compress this hydrogen for 200 bars, we require these installations, the electrolyzer plus the storage capacity, will need very space available. For instance, could be between 60% when compared with a unit of 400 megawatts, the space required for 1 unit of 400 megawatts, to 1.5 times of the space required to implement 1 unit of 400 megawatts. So the storage capacity is very depending of the electrolyzer capacity. The hydrogen is very low volume density, and the space required for storage is quite high. So the hydrogen production should be adjusted to the demand and to avoid higher compression and storage needs. Or the remaining could be doing also to make here some flexibility with the grid, or to other uses, or even injecting the gas pipe and to distribute and to contribute also for the decarbonization of the natural gas.
Paula,
so he
ask you to
okay, it's just to see that we highlight here the layout. The layout of the demo plant is almost freeze. We have 3 containers. We have available 3 containers and a space availability for the storage capacity. Sorry, Ugo, I'm leaving now. Thank you very much for listening to me, and I'm looking forward to hearing the contribution of other panelists. Thank you.
Thanks a lot, Paula. Sorry to we have a tight schedule.
Yes.
I would like to ask you one clarification question. We have, I think, some that were made during your presentation you already answered, but Peter Jansen is asking why compression to 200 bar, much more than what the gas turbine will require, just to keep the tank size at a low level?
Exactly. For instance, for the power plant, we don't need because we inject so we need to inject the pressure in the pipe is almost 38 bars. So we need to inject in 40 bars, no more than. And but this is a question of space. So we should have compress in order to decrease the space. Otherwise, we have a lot of we need a lot of space to storage hydrogen at 30 bars or 40 bars.
Okay. Thanks a lot, Paula. And now I would move to the third speaker, Denis Thomas, from Global Business Development Leader, Water Electrolysis at Cummins, which is a company worldwide leader in designing, manufacturing, building and installing industrial and commercial hydrogen generation. Denis, you will tell us more about the role of Cummins in the project. Yeah, please, the floor is yours.
Yes, okay, thank you. Hello to everyone. I hope you are all safe in whichever place you are. So I was asked indeed to provide an update on the water electrolysis technology that would be deployed in the FLEXnCONFU project. So first, a couple of words about Cummins, because you might not be familiar with this company, which has acquired, in fact, Hydrogenics. So Cummins is a US company, more than 100 years old, specialized in engines, mainly diesel engines for the mobility and the stationary power systems. And over the last 3 years, the company has diversified its activities and has acquired electrification technologies and also battery technologies. And last year, there were several acquisitions made in the field of hydrogen and fuel cell technologies. Concerning the hydrogen technologies that we have in-house, so we have both alkaline and PEM electrolysis technologies. Concerning fuel cells, we are active on solid oxide fuel cells and also PEM fuel cells. And also recently this year, we have formed a joint venture with NPROX in Germany to also have the hydrogen storage tank technology in-house. So concerning the products that were available, in fact, also for the FLEXibilize project, in alkaline and PEM technologies. Alkaline is a very mature technology. That's the one that we manufacture for more than 30 years. From what you see on the left side of this table, those products, they are in the range of 80 kilowatt to 500 kilowatts. And also they have some limitations in terms of turn down ratio. So it's, I would say, the operating window that you can have on those technologies. So we have decided to propose a PEM technology for the FLEXnCONFU project, which is offering quite a good flexibility and dynamic operation, but also it's much more compact than the alkaline technology. And as it was presented just before by EDP, there was a limited space available. So in fact, the product that is going to be deployed is based on what we call the iLizer 500 platform. I'll give some indications now. So the role of the project, obviously, it's to implement the electrolyzer at the Ribatejo power plant that will, in fact, consume electricity from the excess of the power plant to produce hydrogen by using water. You see here a good rendering of the product that is going to be deployed. In the case of the 1 megawatt electrolyzer, there will be only one stack in the system. In fact, the platform to have up to 2 stacks. And then you get all the equipment, gas liquid separators, water polishing system, and all the utilities in one single container. And there will be a second container with all the power components, transformator and rectifier to go from AC power to DC power. This is a visualization of the product that is going to be deployed. This actually is taken from another European project called iBalance, but it will be similar, but there will be certain improvements being made inside the process area of the electrolyzer. Here you see the inside. That's again the inside of the iBalance project, but it will be very similar for the FLEXnCONFU. And here you see the 2 stacks, the 2 PEM cell stacks that are going to be used, and some of the components inside the container. Concerning the platform, it has been already deployed in several projects. So actually the aim of the FLEXnCONFU is not really to do a lot of improvements on the electrolyzer. That's more on the concept actually of operating an electrolyzer in a power plant and then to electrify the hydrogen in the gas turbine. But you see a couple of examples, and I would like also to show you the flexibility aspect of the technology and data which is coming from this project, from the Marcan Energy Storage project in Canada, which is in fact a project which is operated very dynamically. And in fact, we receive a signal every 2 seconds, and the electrolyzer is in fact matching the power consumption with what is actually being asked by the TSO, and we expect the electrolyzer to be operated in a similar way in the Ribatejo power plant. Just to give also some perspective on the electrolyzer technology, obviously there is quite a lot of let's say expectation on our industry today. Water electrolysis is really one of the key technology. Not only at the megawatt scale, but also at the scale of hundreds of megawatts or even gigawatts. So we are, in fact, busy with an upscaling of the technology. So the stack that is going to be used in the FLEXnCONFU, that's the one on the right side, which is a 1.25 megawatt cell stack. able to produce up to 250 noble cubic meter of hydrogen per hour. And the output pressure of the system is 30 bar. That's also one of the advantages of using PEM, is that you can save in the compression of the hydrogen. And what we are doing currently is an upscaling of the stack to actually increase its size by doubling the amount of cells to get a 2.5 megawatt cell stack. And today we are developing another platform, which is called the iLaser 1000 platform, which is the one using, in fact, two of those big or tall cell stacks of 2.5 megawatts. And that's a platform that has an input power of 5 megawatts, able to produce 1,000 cubic meter of hydrogen per hour. And in fact, we are building that product already in a project in Canada. That's in commissioning right now. That's a project together with Air Liquide. And this, I'd say, project looks like this. So in which we have 4 units of 5 megawatts, which are next to each other, each of them connected to one rectifier, and then all the balance of plant, which is centralized. And so if we are thinking about an upscaling of the FLEXnCONFU project, it will be more in that direction that we would go. And that's it. I think I stick to the timing, but I'm available if you have more questions. Thank you.
Thanks a lot, Denis. Yes, indeed. Thanks for sticking with time. We have one question from Alberto Traverso. Given the large size of electrolyzers, what's the use of oxygen? Just vented? Are there practical ways application to exploit the oxygen?
Yes, good question. 1% in which we have electrolyzer just vented, because there is no direct client next to the electrolyzer. But in some cases, and I have in mind a project in Argentina, the oxygen is purified, is compressed, and it is used in hospitals. In some other applications in the industry, where there is a use for the oxygen and the pipe of oxygen is not too far from the electrolyzer, then a connection is possible from the electrolyzer to that system. But in most of the cases, oxygen is rather cheap, and so it's difficult to find a business case if the application is just not next to the electrolyzer.
Okay. So, and another question from Azad Zayud: what is the overall efficiency of the electrolyzer?
Yes, so in this case, we are in the range of, and I think it was presented, I'll just show back, maybe I've been a bit quick on this table. So in fact, we're in the range of 5.1 kilowatt hour per noble cubic meter of hydrogen being produced by the unit. And this is including all the consumption of the utilities. So it includes the water purification, the cooling, and all the auxiliaries. And we always prefer to mention the efficiency in energy consumption by noble cubic meter than in percentages.
Thank you. And the last question is from Michael Ladvik. Why 30 bars? Can it be 40 or 50 bar? In
principle, it could be higher, but then it would require a complete redesign of the unit. Obviously, there is kind of, I would say, it's always a challenge. When you increase the pressure, obviously there's some benefits for the downstream application, but it means that you need to select materials that can handle that pressure inside your electrolyzer. So it makes the electrolyzer more costly. So that's a choice that we made to actually design a product up to 30 bar, and we see some kind of alignment in the industry on that pressure level.
Okay, yes, I actually skipped one question. What is the driver to choose the size of the electrolyzer in the FLEXnCONFU projects? I believe this is the budget, but you can confirm, Denis.
I mean, it was both available budget and also the available space in the power plant.
Okay. Thanks a lot, Denis. I think to move to the fourth and last speaker. Pascal Koschwitz from the Technical University of Darmstadt. Their role in the project is the development of the ammonia reactor. So he will speak about these other power to ammonia solutions. Pascal, the floor is.
Can you hear me? Perfect. So I'll start and I'll try to make it quick, but so that you understand everything, so not too quick. Yeah, I would like to convince you why you should invest in ammonia and not in hydrogen or methane or other chemical storage systems. Okay, let's get started. Why are we talking about ammonia? We're talking about ammonia because we need long-term energy storage. This is from the German Federal Environment Ministry, and they say that for 85% renewables, we want to get 100% renewables. For 85% renewables, we need long-term storage, and for 100%, we need roughly a quarter of what we consume in Germany here, at 2,500 terawatts hours. And we need a quarter of that in long-term energy storage. And ammonia and hydrogen can be a long-term energy storage. And these scenarios take into consideration that we have a European electricity network. So if there's surplus in electricity in Germany, then it can be transported to France, for example. But we still need a lot of energy storage. Yeah. So why ammonia? Well, ammonia has been used in the past as a fertilizer. It's one of the biggest chemicals produced. The infrastructure exists, pipeline exists. It has been handled. There's regulations. Everything is in place already. And ammonia can be used as a refrigerant, is used as an NOx reducing agent. You can make polymers out of it. And most importantly, what I'm going to tell you in the next slide, it's an energy storage. Yeah. So here are the possible 4 renewable energy chemical storages. So we have hydrogen, we have ammonia, and then some people talk about methane and methanol. Let's take a look at the parameters. If we have ambient temperature and a little bit, so 10 bars more than ambient pressure, hydrogen and methane are still in their gas state. And the energy density is very low. Whereas when you compress ammonia a little, you have a high energy density, which compares to liquid methanol. Yeah. But what you have with these two here, not ammonia, methane and methanol, is they produce, when you burn them, they produce carbon dioxide. And once it's out in the air, it's hard to get it back. Whereas these two here, they have no emissions. They have, And these figures here, they show you that when you produce hydrogen, the cost of producing hydrogen is lower than that of producing ammonia. Okay, but when you store it for longer, then the storage costs of hydrogen increases rapidly, whereas with ammonia, it stays very low. So a long-term energy storage will be ammonia, and a short-term can be hydrogen. Yeah, and here are some figures for round-trip efficiencies. Sorry, here are the sources if you want to. They are at the back of the slides. If you take a look at the round-trip efficiencies of producing hydrogen, ammonia, so you see that the same. Of course, hydrogen is the best because out of hydrogen you make the other 3. Yeah, but ammonia compares to them quite well. So yeah, this is my case for ammonia. And this is the plant layout, what we're trying to do in the FLEXnCONFU project. So we have an electrolyzer, a containerized solution, electrolyzer, the reactor is also in the container, and the liquid storage system. And it's placed at the University of Genoa at the Savona campus. And there they have a smart microgrid. So they have PV and everything else for a smart microgrid. And the ammonia is then connected to a gas turbine, and the gas turbine is connected to the microgrid. So it's all in there. So we use excess electricity. We use electrolyzer, produce hydrogen, and then the ammonia synthesis, we produce ammonia, and then it's burned in the gas turbine, micro gas turbine. That's the layout. Now I'd like to focus on the challenges regarding the ammonia synthesis. So this is the reaction that takes place. It's a gas reaction, it's an equilibrium reaction, and it produces heat. Usually the production parameters are 400 degrees Celsius and above 100 bars, and we're aiming at very low temperatures and pressures. We can do that. The problem is we need a good catalyst, or the catalyst is key. At the moment, conventional iron catalysts, they don't work at these temperatures, so we need ruthenium or another catalyst. The problem here is they're quite expensive, and for newer catalysts, the kinetics are largely unknown. And some of the catalysts that are proposed in papers, they're not commercially available. We're working at that, but it's hard to get them. And also with the newer catalysts, you don't know what are the poisons for them. So it might work, the ammonia synthesis might work for a week and then stop because it's poisoned. And we also don't know really what other materials can be used as promoters for the catalyst. So the ruthenium is based on carbon here. So on what other metals, for example, here you barium, calcium. So it's largely unknown, but we're working on that. Yes, but now the outlook in Japan, that's a project 5 years ago. I mean, they are our competitors and they have already shown that it's possible. Now they have done the whole process, the ammonia synthesis with a new catalyst. This one here, they have produced it themselves. They have burned the ammonia, 100% of it. So they have done all of that 5 years ago. This is the reason why I included this slide is not to praise our competitors, but to show you that it's possible. And of course, we'll be better. We have a bigger gas turbine and we'll do things differently. But they have proven that it's possible. Okay, and also I would like to show you that ammonia as a fuel is really is not something out in the sky or something unrealistic. It's realistic, very realistic. This here is a co-combustion of ammonia and hydrogen. That's in the States. That's today. This is also today. This here, the car here, it's in South Korea. This is run 100% on ammonia. And these two pictures here, that's roughly 70 years ago during World War II. That's a bus run by ammonia, run on ammonia. So it's a long time ago and it's possible. Okay, can somebody tell me how much time I've left?
You have a couple of minutes more.
A couple of minutes more. Okay, so I'm well prepared because I didn't know how quick I would be. Yes, some of you may think that ammonia is poisonous. So why do we use ammonia? I mean, hydrogen is not poisonous. It's true. Ammonia is poisonous. At 10,000 parts per million, it's fatal. The good news is that at 50 parts per million, you already smell it. You smell it. So you're far away from dying when you smell it. And the other thing is that if you smell it and if there's a spill, it's lighter than air, so it rapidly dilutes. So that's not an issue either. And what about explosivity? Ammonia doesn't react very well, so the limits for explosion when you mix it with air are far lower than with hydrogen or methane. And when you take into consideration that hydrogen and methane are stored at very high pressures, and then you have an explosion, hallelujah. And the ignition temperature for ammonia is also very low. So ammonia is poisonous, yes. It's also water soluble, but so is methanol. So when you take the competitors into consideration, they all have their drawbacks. So yes, ammonia is poisonous, but okay. The risks are manageable. Yes, I would like to end here because I think we're already over time.
Yes.
Thank you very much. And yes.
Thanks a lot. It was very useful, and that we have some questions. What is the percentage of ammonia and NOx emissions you are aiming for in the demonstrator?
0%. I would like to go to this slide here. They have used ammonia also as an NOx removal. Yeah, so it's possible. Well, they published that the NOx limits are very low, and we're talking about Japan, and I assume that Japan doesn't have very well. They have very low limits. I cannot give you exact numbers, but yeah.
Okay. Next question is, what are the objectives of the project in terms of TRL for the power to ammonia system? Will the 300 degrees Celsius 35 bar system be achieved?
We're aiming for the 335 bars. It can be that we will end up above that, but the 30 bars, for example, we don't know yet if that's really. I mean, if you go up with pressure, that's good for the reaction. That's good for the equilibrium. So I don't really know why we're aiming for low pressures. It can be that at low pressures, it's the components are cheaper. But we don't know that yet. Currently, we're looking for the components, the prices, and it may be that it's we don't have to go down that far. Does that answer your question?
Yeah. Yes, and the next question is, what will be the model of micro gas turbines used for the tests?
The model, the micro gas turbine.
Yes.
Don't know. It's a 100 kilowatts electricity. I don't know what I can show you pictures later on, but I don't have them here. I don't have the data because it's not my. I focus on the synthesis unit.
Okay, I guess it's the T100 from Ansaldo, but
yeah, confirm you go. So the micro gas turbine is the one already installed in Savona laboratory, which is T100 from Turbeck. Now Ansaldo.
Thank you.
And we have a last question. Is there a part on ammonia fuel cells in the FLEXnCONFU project?
No, there isn't, but it's an alternative to using gas turbines. Yes.
Okay. I believe we we are already running out of time. I don't know whether there is a more general question that we would like to someone would like to ask to the other speakers. I believe we had allocated some times in between the presentations. Just feel free to write. We can just take one or two questions more. In the meantime, I also shared with you the link for the third episode. So one question actually that I would like to ask is how easy is to integrate in a power plant those solutions of the FLEXnCONFU in existing power plants. So let's say retrofitting what are the power plants already in operation. I don't know whether Alessandra or Paula, you can
Yes, okay. So
okay, Alessandra, start. You can start.
Yeah. So the main problem related to the retrofitting is related, I think, to two main parts. The first one is on the gas turbine installed in the power plant. So if needed to make some retrofit on that to inject a higher percentage of hydrogen to be burned. So based on which gas turbine is installed and which are the system and the modification to be done to able to burn high percentage of hydrogen. And the second part, the second challenge is related to the space and to the regulatory framework. So of course, when you build from a power plant, you have all the space, you don't have constraints on ATEX, space zone, etc. But when you go to the retrofit part, you have all the constraints related to the existing power plant and the space and how to integrate the power-to-X solution. It's not always easy task. And Paula probably could make more
No, I think Alessandra summarized very well my presentation. It was the main aspects that I focused. It was precisely the assessment of the gas turbine, what percentage that we have to inject, and what are the modifications. And the need for integration, also the control system, because we need to integrate this control system in the existing DCS system and to do all this compatibility. And the space required when we go to a high level of electrolyzer and a high level of hydrogen production. This will be the main aspects. Then the licensing and the safety requirements is almost transversal to all the projects that we implement, and this is typical from the retrofits to address all the interfaces and all the better limits and interfaces with existing power plants. But this, regarding precisely this, it will be the space and the gas turbine assessment.
Okay, thanks a lot. I believe we don't have further questions in the chat. So, and having seen the time, I would like to thanks once again all the speakers to join the session and the participants. And we'll meet for the third episode that will take place on the 1st of December. Thank you for joining, and have a nice day.